is largely part of my postdoctoral work, and I'd like to recognize the truly international team that I had the privilege of working with during that time. My several collaborators and advisors at the University of Tübingen, at Stockholm University, and also at the University of Waikato. If you don't have time to listen to the entire talk or you have to run early, please check out our recent paper in Earth and Planetary Science Letters that summarizes a lot of the results and conclusions that I'll actually be presenting today. This came out, I think, in the December issue, so just a few months ago. Has a very similar title to the title of my talk. So the title of my talk is very intentional, and the title of the paper is intentional. It's based on a prior paper that was written in 1999 and published in JGR by Sean Willett called Orogeny and Orography, the Effects of Erosion on the Structure of Mountain Belts. And I've really enjoyed reading this paper now many times. It's really kind of a cool numerical study that explores the effect of orographic precipitation on the exhumation of a divergent origin, kind of a divergent wedge origin. What this study essentially found is that when you change the prevailing wind direction and you change the amount of erosional efficiency, essentially the erosional efficiency on one side of an origin versus another side of an origin, you can dramatically change both the strain rate and also the amount of exhumation on either side of the origin. So that this suggests that there may be a very strong climatic influence on both the structure and the dynamics of convergent plate boundary origins. This is a figure from this paper that illustrates one of the final results of one of the numerical simulations. So in the upper portion of the figure, you can essentially see the conditions of the model where you have high precipitation rates on the left-hand side, low precipitation rates on the right-hand side. So the left-hand side is characterized by efficient erosion, presumably from an erosion law that takes into account river discharge that is increased with high precipitation, and an inefficient erosion on the right-hand side of the model. And you can see that the model output has exhumed lots of material, as kind of illustrated in this warped mesh on the left-hand side where the erosion is more efficient. That's also the prevailing wind direction, or the wet side of the origin, windward. So this is a very interesting prediction, and as I'm interested in the kind of interaction between surface processes and lithospheric processes, I mean, this is essentially a prediction that climate can influence, like I said, the structure and dynamics of an origin. And so for my postdoc, what I really wanted to do was set out to actually create some observations that we can compare to this model to determine if this is in fact a model that we can use to apply to a natural origin. This is actually an accurate prediction, and really test this model directly. And I have chosen to work in the Southern Alps of New Zealand, which is essentially as close as we can get to a really nice comparison for this numerical simulation. If you're unfamiliar with the area, this is a map of the South Island of New Zealand. The Southern Alps are a linear mountain range that run northeast, southwest on the South Island of New Zealand. New Zealand, of course, is an archipelago nation in the Southern Pacific Ocean east of Australia. The mountains are uplifted along a primary structure called the Alpine Fault that dips to the east. The convergence rate across the fault, or sorry, the fault is effectively a plate boundary between the Australian and Pacific plates, and that plate boundary is highly obliquely convergent. So for about every 4 parts of strike slip motion, there's 1 part of convergence across the fault, and the convergence rate is about 9 millimeters per year presently. And this small component of total oblique convergence is what has created the topography that we see and exhumed the mountains. Very similar to the prescription in the numerical simulation, this mountain range has a strong orographic precipitation gradient, really quite dramatic. If you've ever been there and driven across the mountains, you can see this visibly. So Southern Hemisphere westerlies come from the Tasman Sea, which is to the west, and they blow from the west to the east across the mountains, and very much like a squeegee, the 4 kilometers of topography, or nearly 4 kilometers, basically force a lot of, orographically force a lot of precipitation along the western side of the mountains and not on the eastern side. And so you have a dramatic drop in the total precipitation rate as you move across the mountain range. It's about in some cases, as much as a 10-fold decrease from up to 10 meters per year down to less than 1 meter per year from west to east. And the effect of this concentrated precipitation along the western side of the orogeny has really focused erosion in that area. And there's been quite a lot of studies that I'm not even going to try to list all now. A lot of recent work by Duna Rota too, to really measure these erosion rates. And they're in some cases 5 to 8 millimeters per year, depending on how you're doing the calculation, be it sediment flux or cosmogenic radionuclides. So really high erosion rates along the western side of the orogeny. This rapid erosion has apparently exhumed, or apparently been responsible for exhuming high-grade metamorphic rocks in the immediate hanging wall of the Alpine Fault. So if we were to take a slice through the orogeny and look at its structure and look at its very, very simplistic geology, what we would see is high-grade schist that is exhumed in essentially in the immediate hanging wall, and a metamorphic grade that decreases as you move eastward across the mountains away from the Alpine Fault pretty systematically. One nice thing about working in New Zealand is that there is really detailed and great geologic and publicly available geological maps. So it's really cool just to look at a geological map of this area and see this metamorphic gradient. And so this just the geology itself is apparently consistent with the predictions of this numerical model from the 1999 paper that I began with. Perhaps even more directly, we can look at exhumation rate through the lens of thermochronology. So this is now a plot that shows apatite fission tract cooling ages with distance away from the Alpine Fault along this X to X prime transect. And what you can see is that along the western side of the orogeny, west of the divide, you have very young cooling ages, and that these cooling ages rapidly increase and essentially reach an unreset age component on the eastern side of the orogeny. And they pass through essentially the surface expression of the partial annealing zone. So very young thermochronometric cooling ages west of the divide is also strong evidence for or a strong support for this model that we have preferentially exhumed one side of the orogeny at the expense of the other. Now, many of you may not be familiar with thermochronology, so I just have a few slides to explain how we actually come to this conclusion from this data set, and just a little bit of basics on thermochronology. So to reconstruct exhumation rates and patterns with thermochronology, what we're really doing is not actually measuring exhumation directly. We're measuring mineral cooling during exhumation. And a simple and kind of nice analogy to think about thermochronometers is to think about the minerals that we're dating as little temperature-sensitive stopwatches. And these stopwatches start ticking once that mineral cools below a given temperature, which we refer to as a closure temperature. So I have my mountain range here, and it's raining and it's eroding the mountain range, and temperature increases quite predictably with depth in the Earth's crust. So as we're removing material from the surface and it's being replaced, we are exhuming material from depth to the surface. Here's our mineral. When it cools from a closure temperature of, let's say, 220 C, it gets to the surface, excuse me, and we can go and hike up the mountain, we can collect it, and we can date it, and we can determine the elapsed time since that mineral was at 220 C. So let's say that was 2 million years with an average of 110 C per million year cooling rate. So if the amount of elapsed time was smaller and the age was younger, it would have required faster exhumation. So very simplistically, just comparing cooling ages within the same region, we can say that younger cooling ages typically indicate faster exhumation, older cooling ages indicate slower exhumation. And so this is one kind of relativistic way of looking at patterns of exhumation across an orogeny. So coming back to this slide, again, if you're now looking at this with a little bit more context, the young cooling ages that are within the about 30 kilometers of the Alpine fault reflect very rapid exhumation rates. They are much younger, and the older cooling ages further to the east reflect more limited exhumation and slower rates. If we overlay that now with our rainfall pattern, we can see that there is a very clear spatial correlation between these young cooling ages and very high precipitation rates along the western side of the orogeny. And this spatial correlation agrees with the predictions of this numerical model, and we could leave it at that. But I would beg the question that a spatial correlation is in fact sufficient to really test the hypothesis that there is a climatic control on the exhumation of this orogeny or any orogeny. And I was kind of inspired to go a little bit beyond this spatial comparison from a review paper in 2009 by Kellen Whipple called The Influence of Climate on the Tectonic Evolution of Mountain Belts. And I'm just going to quote 2 sentences from the abstract that summarize, I think, the way that I've been thinking about this. Spatial correlations between intense precipitation or glaciation in zones of rapid rock uplift have indeed been documented in numerous mountain ranges and are consistent with model predictions, like the model predictions that we were just looking at. More compelling evidence, such as a tectonic change in response to, rather than just coincident with climate change, has, however, rarely been documented. And so when I read this and was thinking a lot about this, I think that there's really a value in moving now from spatial comparisons, which have indeed been documented in multiple different orogenic environments, to really looking into the time domain and trying to build temporal records to evaluate this potential causality between paleoclimate and changes in orogeny exhumation. So this is something that I've challenged myself to do, and hopefully will challenge the community, is to do more detrital work, to work in sedimentary archives to build temporal records of rock exhumation. And it's convenient too, because many orogens are surrounded by sedimentary basins, by peripheral sedimentary basins that have essentially accumulated the eroded detritus following the exhumation of that orogeny. So the Southern Alps has very large basins both to the west and the east of the orogeny. Conveniently, this is an island, so essentially the only source of sediment to these basins is coming from the mountains. Might be coming from different parts of the mountains, but it's not coming from like an adjacent landmass. Canterbury Basin is to the east, the West Coast basins are to the west, and there are also several intermontane basins throughout the orogeny which have very nice sedimentary records as well. So I've been working primarily in the West Coast basins, which are some of the results that I'll be showing you today. These basins preserve essentially a complete detrital record that is inverted because it's kind of deposited first with older sediments and then younger sediments at the top. But it preserves a detrital record of source rock erosion rate. So we're always interpreting both the source area, or we're interpreting exhumation of wherever the sediment source was. And so thinking about provenance is also really important when you work in a sedimentary basin. The other benefit to working in a sedimentary basin is that you're often working either in direct records of paleoclimate proxies, like maybe even in the same boreholes, or you're working along the same timescales for really nice paleoclimate reconstructions. So some of our best paleoclimate records come from sedimentary basins as well. So it's less of an apples to oranges comparison than, for example, looking at modern precipitation patterns. There is a little bit of a catch though. So when we work with detrital thermochronology now instead of bedrock thermochronology, we have to account for the fact that our little temperature sensitive stopwatches don't stop ticking after they've been exhumed. Because we weren't there to collect the sample several million years ago, the sample was eroded, it was deposited in a basin, and then that basin filled in. And meanwhile, those little stopwatches have still been ticking. So what we need to do, although the basin preserves a very nice record of source rock exhumation history, we need to account for the fact that those stopwatches are still ticking by separating out the closure age and the depositional age. We do this by calculating something called lag time, and then basically thinking in lag time instead of cooling age or closure age henceforth. So lag time is simply defined as the cooling age minus the depositional age, and these should be determined independently. In the results that I'll be showing, the depositional age is determined biostratigraphically. It could also be determined from magnetostratigraphy or other constraints on depositional age. So essentially the lag time, if you were to define it non-mathematically here, just conceptually, is the time that it takes for a mineral to be exhumed to the surface at the time that it was exhumed. So you're subtracting out the time that it has resided in a basin since it was exhumed. That does not account for the transit time of the mineral from its point of erosion to its deposition in the basin. But in many very rapidly eroding orogens, this is a small fraction of the total kind of cooling age of the mineral, the total amount of mineral exhumation, total duration of time for mineral exhumation. So it may only be a few thousand years of sediment transit, temporary storage in a terrace, something like that, and we're talking millions of years for mineral exhumation. Excuse me, I'm not used to talking so much. So this is a plot on the left-hand side of this image slide that shows essentially a stratigraphic succession of depositional age going from old to the base to young at the top, and lag time on the x-axis from slow on the right to fast on the left. So if we reconstruct this lag time for multiple sedimentary horizons and we calculate the lag time, and it does not change as a function of depositional age, or essentially as a function of time, that indicates that the exhumation rate in the source area contributing that sediment also was not changing over that time. It was a constant exhumation rate. If that decreases over time, then actually what we're seeing is a increase in the exhumation rate in the source area. So as the exhumation rate increases, the amount of throughput gets faster and the cooling age would decrease over time, so the lag time decreases. So this increasing exhumation, or this change that we might see, for example, is really what we're looking for. So a change in the lag time reflects some kind of paleo change in the exhumation rate that might be due to a tectonic or a climatic driver. And this is really what we're interested in something called this lag time study. Okay, so going back to the Southern Alps and thinking about actually finding and targeting a really nice record for doing this kind of lag time study in one of these sedimentary basins. I was lucky enough to be able to collect samples from a borehole that was drilled in the early 1970s, about 14 kilometers away from the Alpine Fault at the mouth of the Waiho River. This is called the Waiho 1. It's primarily a succession of conglomerates and kind of sandy mudstones. The lower, probably third, starts to become calcareous, and then at the very bottom of the borehole, there's a Oligocene limestone that kind of caps bedrock underneath. So the base of the borehole is early Miocene. The biostratigraphy suggests that it's about 16 million years. We have our oldest sedimentary samples are about 14 million years. And then we basically have 23 samples that span the range of time since then. So it's really nice, very proximal deposits. Of course, remember, this is an oblique transpressive boundary. So you have to, going back 14 million years, you have to reconstruct that strike slip change as well. But one nice thing about this borehole is that there's independently been provenance constraints that have been determined from looking at the lithology of conglomerate clasts and cuttings kind of independently of where the cooling ages have been sampled. So for the majority, something like 80% of the borehole, there's a predominance of source areas in hanging wall terrains of the Alpine Fault. This is, if you're familiar with the terrains of New Zealand, this is the Torless terrain. It's a greywacke. There's a lot of greywackies in New Zealand, so it's tricky to sometimes distinguish exactly which greywacke it is, but the provenance analysis is pretty conclusive that most of the sediment was coming from the hanging wall and not from, for example, footwall blocks that may have been uplifted at that time. Also, another interesting thing to notice is that this high-grade schist that's exhumed in the immediate hanging wall of the Alpine fault that I mentioned earlier, that appears about 4 million years ago in the borehole sequence. So that's also a marker that we can use just lithologically to indicate that there had been a significant amount of exhumation by that time. So we have a nice a densely sampled stratigraphic record that has independent constraints on sedimentary provenance and biostratigraphy constraints on the depositional age. And what we can do is collect a sample from the borehole and do detrital thermochronology. We separate out different minerals for dating, and we might date a subsample of those minerals, like 100 grains or 150 grains, or in some cases even more than that, depending on the sample and how simple the distribution is. When we have a distribution of these ages, it's not as simple as just taking a mean, because they are typically multimodal distributions and they reflect different contributions from different parts of the catchment that have different thermal histories. So this is an example of a detrital zircon fission track cooling age distribution that was published for the Hokitika River. So it's a modern sample, just what you would see today. Oops, sorry. And in the modern sample, you can see that there's a very young age component that has about 5 million year peak age. And then there are also older age components that reflect some degree of partial annealing or even fully unreset grains that are also within the drainage area. And of course, the drainage area could be changing over time. This could increase in the amount of various grain age populations. So what we want to do when we make a comparison between different stratigraphic horizons is systematically compare the same component. And the simplest and probably most straightforward thing to do is to compare the minimum age component, because that reflects the most rapidly exhumed part of the catchment. In the case of the Southern Alps, this is the part of the catchment that is adjacent to the Alpine fault that has been most deeply exhumed. At least this is our assumption. So we're consistently comparing our minimum age lag time component. This is a cooling age component because it's a modern sample. In the borehole sequence, it'll be a lag time component. Okay, so these are the primary results that we have put together for two different thermochronometric systems, both fission track, but for apatite and zircon minerals. So the yellow are zircon fission track results, and the blue are apatite fission track results. You don't really need to know the details for what fission track means versus other thermochronometric methods. You just should know that zircon fission track has a slightly higher closure temperature than apatite. So it's accessing a slightly deeper part of the upper crust, and it's responding to a change slightly later than apatite, which is shallower, and it would respond a little bit sooner to a change in exhumation rate. So on the, this is essentially the same plot that we were looking at when I was explaining how you calculate lag time. On the y-axis is depositional age in the borehole. This is determined through biostratigraphy, and on the x-axis is the lag time that was calculated. So this is not cooling age components, but just lag time directly. You'll notice that I have some negative numbers in the x-axis, and that's because in the lowest 3 samples, the minimum age components are actually negative. That means that the cooling ages are less than the depositional age. And this is something that can happen when these minerals have been reheated diagenetically in a basin. So they're accumulating radiation damage, but they're also being reheated as they're buried further deeper and deeper into the basin. And in our paper, I don't show the plots here, but we can demonstrate that these diagenetic temperatures were sufficiently high that they actually access the kind of lower bound of the apatite fission track closure temperature and partially annealed and reset some of the grains. So for these lowest 3 samples, the minimum age component that is not clearly reset is what is plotted. That's not the X plot, but the little dot. So the clear trend that you can see here is that lag time is relatively old in the lower portion of the sequence, and then rapidly declines or decreases and becomes much younger in the upper portion of the borehole. And so in apatite, this is a relatively rapid change, and in zircon, it's a little bit more of a slower change. And that qualitatively, the time when this changes is about 6 million years ago. That's stratigraphic horizon, just qualitatively. But we actually would like to interpret this quantitatively. So what we did is set up a inverse thermal modeling approach that accounts for the advection of isotherms and basically the advection of heat during the exhumation of the source area. If you have a change in exhumation rate, you're going to be advecting a different amount of heat than you were previously. You're going to actually change the closure depth, and you need to account for that when you do any kind of exhumation rate reconstruction. So we used a one-dimensional model. This is a relatively simple approach implemented in an inverse neighborhood algorithm that efficiently is searching for a kind of the best fit model by randomly sampling a series of different models, comparing them to our observations, trying different ones, and doing that iteratively until we converge on a solution. So the models seem, so what I'm plotting here, these lines overlaying are actually just a bunch of different model results and showing how kind of, I think these are kind of like the top 10% of what I actually ran, just to illustrate the degree of fit that we are able to achieve with our dense data set, which is actually pretty good. So quantitatively, what we observe is that a exhumation rate change at 7.4 million years is kind of the best model to explain this late Miocene change in cooling ages, or sorry, in lag time that we observe. And this isn't at 6 million years, right? It's a little bit before that, because you actually have to exhume, after there's a change in exhumation rate, you have to exhume the existing topography in order to see that emerge, that signal emerge in the sedimentary record. There's a little bit of a lag, and it's like a lag in lag time. I keep saying that word, but so that's why it's not exactly as what it appears in the sedimentary record. Some other interesting results that we produced, this is a little bit later after kind of we had done all the fission track dating, is we were curious if we could double date some of the zircon grains with uranium, thorium, helium, which is a different technique, but the same mineral, also a slightly lower closure temperature. So what I did is I basically cut some of the zircon grains that had been mounted for fission track out of the mounts and imaged them, and then repackaged them for helium degassing and ultimately dissolution for uranium thorium measurement and calculating a uranium thorium samarium helium age. So if anybody who's listening has done helium analyses, you know that you have to account for diffusion of helium out from the exterior of the mineral, and you need to know its surface area volume relationship pretty accurately to do what's called an FT correction. And this is complicated when you have only half of the grain and the grain might be irregular. So we developed a really interesting approach that I'll just briefly advertise for looking at partial grains and irregularly shaped grains, where we took multiple perspective microscope images of the grain and then made a 3D model of its surface, which allowed us to calculate the surface area and volume ratio quite precisely and do it relatively rapidly. So we could do it for a large number of grains. And it was a really cool approach and allows us to simulate, also the effect of basically cutting a grain in half for fission track dating and the effect that has on the FT correction. So the results that we have now for multi-dating individual zircon grains, this is now a similar plot, except instead of looking at lag time, we're looking at cooling rate. And I calculate this cooling rate by simply assuming an initial geothermal gradient. It's not totally an assumption, it is independently constrained, and then allowing that geothermal gradient to increase to the gradient that we observed today, just linearly. This is not a very complicated model, and it could definitely be improved on just kind of new preliminary results. And I did this for about 3 to 5 grains per sample in the samples that we were able to easily extract zircons from, and those are the ones that are plotted. So what you can see is at the time when you had older cooling ages in the lower half of the borehole, you also have slow cooling rates, excuse me. And that these cooling rates increase after around 7 million years, and then possibly in the upper 2 samples come to some kind of plateau, but it's just 2 samples that we're comparing here. So it's not sure exactly if that's a real signal or not, but it's clear that cooling rates increased in the late Miocene around the same time when cooling ages decreased. So this is a nice external check on our primary data set. Okay, so now I can kind of piece together a full exhumation history of the Southern Alps and compare it to independent tectonic and climatic records over the same timescales, building a temporal record to really test the hypothesis that there was a climatic influence on the exhumation history of the origin. So what I'm going to do in the next few slides is basically layer on different data sets, and I'll try to do this slowly because it's a lot of lines. I'll layer on different data sets, and you can just make a comparison visually, and I'll explain my interpretation of the data. So the y-axis here is time or age, depositional age in the borehole. The borehole stratigraphy records a period of erosion and non-deposition right above this basal limestone that was the Oligocene that encompasses a large part of the early Miocene. And then starting about 15 million years ago, you have calcareous deposition. It moves into siliceous deposition, or it was really kind of muddy calcareous, but then you move into this coarser grain deposition through the mid to late Miocene to the present day. As I mentioned, there's also provenance constraints in this borehole that indicate through the majority of it, you have this hanging wall terrain derivation and then schist that appears within the last 4 million years. Also from the borehole itself, we can calculate the subsidence history by using the same biostratigraphy. And when we do that, this is discretized, so it's not a nice smooth curve, but we do see that there's an increase in the subsidence rate in the kind of late Miocene to Pliocene, starting around 6 million years or so. Excuse me. So next is that I would like to present is the results of our exhumation history inverse modeling. So these are the best fit models, assuming different prescribed number of rate changes. So in our model, we did not prescribe the amount of exhumation rate, like the magnitude of exhumation rate change or the timing, but we did have to prescribe the total number of rate changes. We couldn't just assume this. And I explored scenarios with 2 to 4 changes in rate. And really the results are pretty robust and don't depend so much on that, but there is some slight differences for a period of early exhumation in the early Miocene. So for basically the red, blue, and yellow lines, these all reflect either 2, 3, or 4 rate changes. There is a consistent change in rate at 7.4 million years. And then there was also a period of rapid exhumation in the early Miocene between 20 to approximately 22 million years that may be kind of a pulse of exhumation. It appears that there was a short period of high exhumation rates. And that is constrained essentially by fitting the lowest 3 or 4 samples of our data set, basically fitting what sort of exhumation rates would have been explained to create those ages. It's not as well constrained as the 7.4 million year change, and consequently, there's a little bit more uncertainty in the timing. I also explored relaxing the assumption of a instantaneous rate change, and basically a step function. If we do that and we just kind of have a gradual change, it has a sigmoidal curve. This is illustrated with the light red line. We really don't see much of an influence of that. That whether or not it's a step function change or a slightly gradual change is really a second order effect that is very difficult to tease out from our data. So really we can constrain the timing of rate change, but not necessarily how rapid that rate change evolved at the time that it occurred. It's just a really hard thing to do. The dashed line is basically a somewhat extreme assumption that our biostratigraphic depositional age model is totally underestimating the true depositional ages. So that takes kind of like I said, a kind of extreme view that all of the samples were deposited at the earliest possible age for that biostratigraphic zone. So it's kind of a one extreme end member alternative for our biostratigraphic depositional age model. Again, the timing for what we're looking at in our exhumation history reconstruction really comes from biostratigraphic control. So I'm just playing around with taking an extreme end member to that. It's not actually what I would think is the best interpretation of those results. And indeed, we even ran some additional biostratigraphy in the last 6 months that that suggests this is not the case, but it's just to demonstrate that even in the most extreme case, we would change the timing of this late Miocene exhumation event by about 2 million years to 2.5 million years. Again, the precise number of the actual rate changes depends slightly. Oh, sorry, the precise timing depends slightly on the number of rate changes as I described, but it's quite a robust model. These again are all the best fit models. So let's compare this now to a tectonic reconstruction of the Australian Pacific plate boundary. What I'm showing here are boundary perpendicular convergence rates. So this is the boundary perpendicular component of the total convergence across these two plates that have been reconstructed in a really nice publication by Candy and Stock in 2004. So their actual the actual data that goes into this is essentially the vertical black lines, which are average convergence rates over the chron duration. So like the let's see, the 2AY chron is 0 to about I can't remember exactly, almost 3 million years. And then they basically have an average over that duration. To try to refine that initial data set, Kevin Furlong and Peter Kemp in 2009 essentially developed a constrained interpolation that uses reasonable motions of the plates to basically fit these data sets or fit this data point. And so that's what the red line is. It's an interpolation. It's not truly new data. It relies on the same initial data set, but it helps us to interpret likely how this change actually occurred. It was likely a gradual change in convergence rate rather than like an abrupt change in convergence rate. So one interesting thing is that at 7.4, or if we take the extreme end member in our depositional age model, 9.9 million years, there's no abrupt tectonic changes at this time. There have been previously in the literature proposed an abrupt change in convergence direction at 6.4 million years, but that relies on a very old interpretation of an old plate reconstruction. And it's actually discussed very deliberately in the Candy and Stock paper. So if you're thinking about that possible alternative, I would encourage you to read this Candy and Stock paper first. And then also, we see a clear change in or some kind of tectonic change 20 to 22 million years ago. This coincides with essentially the initiation of convergence across the plate boundary. It's essentially the emergence of the alpine fault as a convergent structure, which is really interesting. It seems to be a very clearly tectonically related signal. And one idea that I've been thinking about is that this pulse of exhumation that is preserved, or at least interpreted in our exhumation history, could actually reflect inversion of pre-existing extensional basins. So basically, prior to convergence across the alpine fault, you had a period of extension and you had sedimentary infill that filled in basins at or below sea level. And then as soon as you start to change that extension to convergence, you're going to basically uplift and invert all of the sedimentary infill, which would be very easy to erode and might explain why you had very rapid cooling at this time. So let's now compare the tectonic reconstruction to different climatic and paleoclimatic proxy records. So the first one that's in blue is the paleolatitude of the subtropical front. This is essentially a proxy for where the westerlies may have been. It's very difficult to reconstruct a paleo wind pattern over millions of years. So the subtropical front is an oceanographic front that is essentially aligned with, possibly driven by, westerlies. And so we can use it essentially as a proxy for the paleolatitude of the westerlies. This is a record that was built through looking at sediment cores, basically south in a transect south of New Zealand, moving north towards New Zealand. Over from about 15 to about 11 million years, you had these subtropical front rapidly move northwards towards and reach the southern margin of the New Zealand landmass. So this may be evidence for northward migration of the southern hemisphere westerlies in the late, kind of mid to late Miocene. But it's clear that the westerlies were at the same latitude as the paleo Southern Alps, as the paleo New Zealand landmass prior to the change in exhumation rate that we see. Two other proxies for paleo kind of westerlies are dust flux coarseness. This is from a record from the South Pacific, and also the amount of sediment discharge from the Australian or to the Australian shelf. This is interpreted to be kind of a paleo wetness versus dryness record. And these both increase from about 11 to 7 million years. And I would argue that basically this is a period of strengthening of the southern hemisphere westerlies. It may be that the westerlies migrated and then changed in their intensity. It'd be interesting to compare this to any more recent paleoclimate records, if some exist. And that I would argue that essentially this is the time when we start to develop a rain shadow with whatever paleotopography pre-existed in the Southern Alps. Onshore, so the terrestrial paleoclimate records change after 7 million years. This is a time, the New Zealand stage is called the Capetian, and this is a period of very cool, wet paleoclimate proxies. And I would essentially indicate that that is the establishment. What's being recorded in the paleoclimate record is the establishment of the rain shadow. And then it's interesting because it kind of goes back, and then in the Pleistocene it comes back again. I don't know maybe what might explain that, but it is interesting that our change in exhumation rate coincides with this regional change in terrestrial paleoclimate. So just to summarize everything on one very complicated slide, the broader interpretation that I'm making here is that, if we were to build an entire history of the Southern Alps, is that basically the Alpine fault convergence started around 23 MA, and as that convergence began, you had a period of inversion of pre-existing extensional basins that led to a pulse in exhumation that's preserved in our cooling ages at the lowest part of the borehole. So this is this 20 to 22 MA exhumation rate increase, or pulse of exhumation. There's some additional data that suggests that there was crustal thickening that went on as the boundary normal component of plate convergence increased. So the amount of plate convergence is increasing. You're getting more and more tectonic flux to the origin, but you're not seeing an exhumational response. And this may be that you're basically just creating a very large, wide origin that was under a relatively stable climate and was not really being extensively eroded. And you were just simply thickening the crust and not actually exhuming it, possibly increasing topographic, the paleotopography as well. There's also some evidence to suggest that there was paleotopography in the kind of earliest late Miocene. And then at some point in the late Miocene, around 7.4 million years, there is a threshold change in the erosional process of the origin that allows you to remove large amounts of material that is then deposited, increasing the subsidence rate of the Foreland Basin in the west coast, or on the western side of the origin. This is coincident with the regional change in climate that I would propose is essentially the establishment of the orographic rain shadow that we see today. But I think there are other interesting theories to play around with, that this could be an early period of glaciation if you had kind of threshold topography that could start to accumulate glaciers. There's no direct record of that, but it's an interesting thing to think about. And there are some other ideas I think that we can play around with in terms from a geomorphic perspective of thinking how you might have this rapid change in geomorphic rapid change in erosion rate that reflects like a threshold change in geomorphic process, like a transition to glaciation, or maybe a attainment of threshold hill slopes or something like that. So just to summarize the take-home messages for the new results that I'm presenting, the Southern Alps essentially have a two-phase exhumation history. In the early Miocene, 20 to 22 million years ago, there was an inversion of pre-existing extensional basins that led to a rapid pulse of cooling. And then there was essentially very little exhumation since that time until about 7.4 million years, when you have sustained rapid exhumation that basically turns on. And I would propose that is coincident with the development of orographic precipitation. If it is true that that is coincident with the development of orographic precipitation, then the temporal record and the spatial record of exhumation of this origin are consistent with this original model that suggests a climatic influence on origin structure and dynamics that was originally proposed in 1999. So I would argue that both of these records, in fact, do support that. But I still think that there's a lot of room to kind of work out the details, particularly thinking about the geomorphic thresholds that might have led to a very rapid change in exhumation rate in the late Miocene. And with that, I'll just say thank you very much for listening. Looks like I went over time a little bit, apologize about that, but I'm happy to take your questions. And please, if you're not comfortable asking a question, just get in touch with me directly. I put my email and my Twitter handle up here. And I also want to mention that I'm actively building a group. So please get in touch if you're interested in graduate or postdoc opportunities. I might have some coming available in the next year. It's not the right time this year to be applying, but it is something to stay in touch about for the future. So thank you.
Great. Thank you so much, Karl. That was really, really exciting stuff. So what we're going to do now is the chat is open for questions. I already see we have a couple in there. I will start by reading the first one of those out and we'll just go down the list. Additionally, if you would like to, you are welcome to unmute or to rather put your hand up and we can ask you to unmute and share your question directly. So for the meantime, I'll start from the top of the chat. So the first question is about rock type, and it's basically asking how would I suppose the thermal modeling is what they're asking about, change if you're talking about, well, actually, I'm not sure. If you understand the question, have at it, Karl. How would the modeling change if you're talking about working on sedimentary rather than meta-sedimentary rock? Otherwise, I might ask the asker to clarify.
Yeah, I'm not exactly sure. I think that what really goes into the model is the PQ does not really care so much about the lithology of the rock. It's really just the thermal parameters of the rock. So if those are changing as a function of time, then that is something that would matter, like if the conductivity of the crust is changing, or I guess diffusivity, but well, I did not consider that. I have not really considered that before. It's an interesting thing to think about, like as you exhume through different types of rock, you're changing the diffusivity of the crust, and you could have like a layered model or something. That's an interesting idea. I have not done that.
All right, so I'll ask the next question. It is from Monica Russman. Do you think that seismic events like volcanic eruptions have any impact on erosion rates because they can cause large magnitude of landslides and intense erosion and deposition?
So on the timescales that I'm considering, this is kind of averaged out unless, so really what I think would be important is if in the seismic cycle, there is a change in the frequency of large magnitude seismic events that happens over millions of years or something, like basically the activity on one fault increases versus other faults. So yeah, on a million-year time scale, individual events, I don't know that would necessarily be as significant to the actual erosion of the source area, but it might be really significant for the preservation in the sedimentary record. Like I often wonder if we're looking basically at event deposits and turbidites and these offshore boreholes or in any real basin, you might be really biased to very large magnitude events. But even at that time, I don't think that would be a big problem. It would just be kind of a bias in the depositional age model of the sedimentary record and not really a bias in the actual exhumation of the source area. That makes sense.
Okay, I can go with the next question from Rachel Bosch. What do you think is a similar analysis of sediment from the basin to the east of the Alps might contribute to your story?
Let me chime in a minute. I corrected myself. I meant to the west.
You meant to the east or to the west?
East, right? We found, I think Pierre got it right. We found the correction further down.
Yeah, I found the correction, so I updated the question. Thanks.
Okay, thanks.
So the record that I was looking at was from the west of the origin, and I think you're saying in the Canterbury Basin to the east. So I have done this actually. I have done detrital thermochronology from intermontane basin deposits on the eastern side. I don't have any deposits from boreholes on the east side, although I think some other folks have been doing that. And The problem there is that there simply has not been sufficient exhumation to really reset anything except for apatite helium, and apatite helium ages are not reset prior to like Pleistocene deposits. So anything older than that, you're just looking at old inherited ages that do not really record an exhumation signal. So it would be really interesting, I think, to look at sedimentology of those boreholes. If there was some way for you to do very low temperature thermochronology, like detrital OSL thermochronology or something, you could maybe consider that. But our lowest temperature kind of conventional thermochronometers are not really applicable to those deposits because they just don't record very much exhumation.
Okay, thanks.
Great. So I'll take the next one from Duno Rhoda Baluta, who's saying, great talk, Karl, thanks. You mentioned that the Waiho core shows an upward coarsening trend. Does the timing of the coarsening trend coincide with the inferred increase in precipitation and hence river discharge?
Yeah, it probably, it's also reflecting increased proximity to the source area because you're basically the borehole was offshore moving slightly onshore, but highly obliquely over time. So you're both moving the actual depositional center towards the source area, which would increase the grain size, and then probably increasing the grain size of the sediment that's being evacuated from the mountains. And I don't know if you could disentangle those two, possibly. But I wouldn't hang my hat just on one explanation for that grain size trend.
All right, so I'll take the next question from Ed Roth, which is at 6.6 million years ago or so, there was a significant change in the North American Pacific Plate relative motion. Could that be related to the change at 7.2 million years rather than simple climatic change?
Yeah, so this is a very good question. And I know that this Pacific Plate motion change is well recorded in other areas of the other Pacific Plate boundaries. And I just don't know how well it's actually recorded in this part of the Pacific Plate boundary. I mean, I think it'd be really interesting to try to do more detailed plate reconstructions at this time in New Zealand. I don't actually know how that we might go about doing that, but I don't want to throw out the idea that there was a change in plate convergence direction and thus also perpendicular component of convergence velocity at 6.6 or 6.4 million years. It's just less consistent with more updated plate reconstructions for this part of the Pacific Plate boundary. So I know that there's other evidence from other parts of the Pacific Plate that suggest there was this 6.6. I mean, it could be that basically the change was felt earlier at 7.4 in New Zealand. I don't have an easy explanation for that, but that could be something that we look into with new approaches and new data.
Great, thanks very much, Karl. That's great.
Okay, I take the next question from Peter Vanderbeek, who will say nice talk and very nice work. So I think you can guess what he will ask you. Do you actually need a climate change to explain the detrital thermochrone record? Or could you alternatively argue that you are seeing the mountain bed reaching a threshold elevation to set up the orographic precipitation?
Yeah, so thank you, Peter. It's good to hear from you. You're right. It could be that this is a change in geomorphic process that is independent of climate. I think it could equally be true that it is a change in geomorphic process that is dependent on climate. I have proposed the alternative, and I don't know how we could necessarily reconstruct paleotopographic elevation, or really, I guess, like fluvial relief over time. I think that would be kind of hard to do. So I think, kind of within the confines and the objectives of the study, I'm arguing that it's a climatic shift because we see contemporaneous changes in paleoclimate record at the same time as the change in exhumation rate. So it's possible that theoretically they don't have to be related, but they appear to be correlated. I guess, I don't know if that's a sufficient answer, but yeah, you're right that it is possible that it could just be that you achieve a threshold slope, like for example, threshold hill slopes that increases the erosion rate dramatically, that's independent of climate. But I think there's clearly got to be a climatic element to it.
Great. Okay. The next question is from Doug Burbank, who's asking how do the modern detrital thermochron records compare on the eastern versus western flanks of the range, and what do these contrasts suggest?
So you mean the detrital thermochronology of modern rivers of the same system? So there's a very nice John Garber did a nice study of this, presented work in a paper, I think with Peter Camp and another paper with Matthias Brené in the mid 2000s that shows some data here. So along the western side, you basically have very young cooling ages for apatite and zircon fission track, and of course lower temperature thermochronometers as well are going to be at least as low. And the surface manifestation of the zircon fission track partial annealing zone is effectively the drainage divide. That basically, when you then look on the the eastern side of the origin, you basically get unreset zircon fission track ages in modern rivers there. So it's not as useful for interpreting paleoexhumation rate or something like that. Now with apatite fission track, the partial annealing zone, or it's not really the partial annealing zone, but like the surface expression of the partial annealing zone at depth, is actually exposed in the mid portion of the eastern part of the of eastern drainages, like the Rangitata and the Rakai and these very large river drainages. And actually, you can use the change in apatite fission track age as a function of distance, away from the alpine fault and across the mountains to try to reconstruct where those detrital cooling ages came from. I have a paper that did that in 2018. If you are interested, you should check it out. But I hope I'm answering the question directly. But basically, what it indicates is that as you have exhumed material in the hang wall of the alpine fault, you have this gradient that moves eastward away from it. Very high exhumation near the fault, very low, and ultimately very little exhumation further to the east. Oh, my headphones started to talk to me. And so anyways, as that occurs, you basically lose the ability to interpret. You don't have sufficient exhumation further to the east on the eastern side of the origin to say much using these systems. You'd either have to use a very low temperature system. But yeah, I think I don't know. I'll stop there. Ask me if that didn't answer your question. I noticed that Peter Vanderbeek said that there's some stable isotope evidence about the rain shadow setting in at that time. I think he's referring to the Chamberlain article paper about that. That's true. Actually, something that I didn't mention is that I've done a lot of compound specific stable isotope work in similar sedimentary deposits on both sides of the origin to try to test this as a function of time. And it's been very difficult to do that work using leaf wax hydrogen isotopes. There's a lot of problems with that. So I have tried to do that too, and I've had mixed results. One thing that's really interesting is that the actual leaf wax hydrogen isotopes in modern surface deposits, just like in sediment that's collected along the margin of a lake or along a riverbank, really nicely preserves in the isotopes, it preserves the signal of the rain shadow. So like you see something like a 30 per mil shift in hydrogen isotopes just by moving across the rain shadow. I think I had some abstracts on that. I'm hoping to get that out soon.
Great. So I think the last question is just sort of getting at what we've been discussing for the last few minutes, which is whether we can attribute these kind of phases of exhumation to tectonics or climate. But that brings us to a little after the hour, so we'll let it stand there. Thank you all so much for coming, and thanks again to Karl for a fantastic talk. And don't forget, we've got 3 more talks in this series over the next 3 weeks before we take our break. So thanks everyone, and we'll see everybody next time.
Thank you.